Okay, so let's get started. And I'll spare you those long and boring academic introductions. And I'll just say my name is Gabriele Carcassi, and I lead a project called Assumptions of Physics that aims to find a minimal set of physical assumptions from which to derive the laws. And I've been doing this for about 10 years. And so tonight I'm going to share with you what I've learned about the fascinating, preposterous, and really sad word that is the foundations of physics. As you have noticed, I'm playing the piano, and I'm going to do this for three reasons. First, if I just stood up and read from a tablet, it wouldn't look nearly as professional. And second, it kind of helps create a mood, and everything that I say sounds so much more insightful. And third, it immediately signals your subconscious that I am a skilled person. And therefore, everything that I say, you will trust, right? Oh, he can play the piano, he can talk while playing the piano. Surely he knows everything about physics and mathematics. And even if I told you that you're being manipulated, it really doesn't matter. You still think that I look very professional, that I say insightful things, and that I know what I'm talking about. So I've always been interested in math and science, and at the end of high school, I was an avid reader of the Italian edition of Scientific American. And at the time, they ran quite a bit of articles on the interpretations of quantum mechanics. And I found them fascinating. I mean, our most fundamental theory is not fully understood. The state, the wave function, is given in terms of complex number and is not exactly clear what they represent. And during a process, the state evolves deterministically, but then, during a measurement, the rules are different. The state changes abruptly, the wave function collapses. And the measurement outcome can only be predicted by a probability. And the properties of a quantum system then are not always fully defined beforehand. They can be in a superposition state, where the value is undecided and the future evolution of the system is uncertain. Where will I be tomorrow? Which path will I take? Will it bring joy or sorrow? What am I putting at stake? Should I change my direction or make a minor correction? Am I coming or going? There's no way of knowing a future I've yet to decide. 'Cause I'm in a superposition state. I'm in a superposition state. There's so much on the plate, so much to debate in a superposition state. And so the quantum world has an intrinsic uncertainty to it. And unlike the classical world, only averages, expectations are well defined. What are my expectations out of this world that we live in? Will all these random fluctuations decide what I am given? Will I open the curtain and see if my future's uncertain? Is my destiny written? Am I saved or smitten? Is my will still free to decide? Since I'm in a superposition state, I'm in a superposition state. There's no early or late. Decisions can wait in a superposition state. And so, to make sense of all this, people created different interpretations. Some claim that there exist hidden variables that determine the output of all experiment, but these are experimentally inaccessible quantities that are hidden from us. Some claim that during a measurement, the universe itself branches off into different separate universes where each possible outcome is realized, infinitely many worlds in which anything and everything happens. Others claim that consciousness itself causes measurement to happen. It is our act of looking that changes reality. And the reality is created by this back and forth between mind and the universe. And others claim that it's all about agents tracking subjective information, that the quantum state does not represent physical reality, and the rules of quantum mechanics are simply bookkeeping for that subjective information. These are very different views, and they're all compatible with quantum mechanics. And you can choose your view: hidden variables, multiple universe, consciousness, subjective realities, and all of this is fascinating. And I remember pondering all of this when I was younger. All these possibilities, no way of knowing which one is true. And I remember coming to a startling conclusion. I don't think this makes any sense. I mean, I thought that science, that physics, is about the things that you can prepare in a lab, things that you can measure, things that are experimentally accessible. But these things, these interpretations add things they're not in the equation, and they're not really experimentally well defined. I mean, how do you define consciousness experimentally? I went to a lab and I prepared 3 consciousnesses. That doesn't work. Or subjective reality. So I make an experiment and you guys see something else? That also doesn't work. Or hidden variables, right? They're there, you can't see them, you can't prepare them, you can measure them, but they're really there. Or a parallel universe in which other things happen, but how do we know that they even exist? I mean, it's interesting because I find people that reject the idea of God because there is no experimental evidence for it, and then they go on and on about parallel universe and hidden variables. And look, if you like contemplating these things, it's fine, right? But the problem is that they're never going to tell you anything about the physics because the physics is experimentally accessible. And one thing that I noticed while talking to people that are interested in interpretation and the foundation is that most of them are not really interested in understanding quantum mechanics per se. They're really interested in understanding the universe at a fundamental level. What are the fundamental objects? How do they work? And so on. And the issue is that quantum mechanics is not really about fundamental objects. I mean, for example, let's turn this on, which is going to work better. There we go. Let's take an electron. And we do use the rules of quantum mechanics to study it and to see how it interacts and interferes. But the same rules apply to a proton, and a proton is not fundamental. It's a composite object. We can study an atom and see how it diffracts and interferes, again using the same equation, and this is even less of a fundamental object. Even a complicated molecule like this is called a buckyball, and it's shaped like a football. Well, everywhere in the universe is shaped like a football, except in the US, it's shaped like a soccer ball. But even this object follows the same rules. So you have the same rules for all these objects, and most of them are not fundamental. And come to think about it, even the electron, how do we know that it's really fundamental? I mean, we thought for a long time that the proton was fundamental until we were able to prove the internal structure and see that it was internal structure. So the only thing that we can see about the electron is that we haven't found any substructure yet. So if quantum mechanics talks about all these things, and most of them are not fundamental, if I understood quantum mechanics, I would know why I would use the same equation in all these cases, but I wouldn't really know anything about fundamental objects. And I talked and I said these to some people that work on interpretation, and they tell me, Gabriel, you have a point. And then they completely disregard this and go back to talk about fundamental objects. So it was clear to me that I personally was not interested in fundamental objects. I was really interested in just understanding what the rules of quantum mechanics is, what is described. And so in 1998, I was a summer student at CERN, the lab in Switzerland with lots of chocolate, a big particle accelerator, and a big library. And I thought that what I was interested in would be likely in the first couple of chapters of a physics textbook. And so I started reading lots of quantum textbooks, and they were roughly three approaches. The first one was the most popular one, the historical one, with the black body radiation, the photoelectric effect, the various models of the atom. And the second was the mathematical approach, where there are the postulate, there is this math, the Hilbert spaces, and this is how you use it. And the third one was the Feynman approach. You basically say every measurement is probability, and then you introduce this complex version of probability, the probability amplitude, and you go and derive some things. But all these books followed one of these three approaches, patterns, and none of them said what a quantum system actually was and why should I model it that way. So I'm still at CERN at a summer school, and there are lots of bright people and knowledgeable people. So I started asking a lot of questions, and I got many replies, but not many answers, until a student older than me told me, look, nobody has a clue. The only thing that we have is the math, and I can teach you the math. And he was right. The only thing we have is the math. So I learned the math like any other physicist, badly. And I understood how to use the math to solve problems, and I got to the understanding that most physics have, but I was not satisfied. There was still something missing. There was still something missing. Because there is a tiny problem with math. There is a tiny problem. Let me give you an example. So let's get this equation, F equals ma. Most of you are going to recognize it. But you see, F is just a symbol. And I haven't told you what the symbol stands for. You used your English bias to understand that there was a force. But suppose I told you that voltage in Italian is farrone. Now, this would be a lie, but most of you wouldn't know. So F would be voltage, M would be resistance, and A could stand for current intensity. And so this would be Ohm's law. It wouldn't be Newton's law. Or F could stand for temperature difference, M could stand for the R value of an insulator, and A could stand for heat flux. And now we're talking about something else. Or F could stand for pressure. There are dozens of these. And it's because all that this equation is describing is a linear system. And all systems for small fluctuations are linear systems. And that's why linear algebra is so powerful. So if I only told you F equal ma, the only thing that you actually know is that the symbol on the left is equal the product of the symbol on the right, and that's it. And this is the problem with math. It's meaningless. And it's not really a joke. This is not something that I say. This is something that people much more important than me say. For example, David Hilbert, one of the greatest mathematicians, the brain the size of a skyscraper, he said, mathematics is a game played according to certain simple rules with meaningless mark of paper. You see, I'm not saying that. David Hilbert is saying that. And Bertrand Russell, one of the greatest philosophers, right, the brain of the sign of skyscraper, he says, it is essential not to discuss whether the first proposition is really true and not to mention what the anything is of which it is supposed to be true. Again, this is not me, right? This is Bertrand Russell. And one of the greatest thinkers of our time said, mathematics knows the rules of everything and the meaning of nothing. This time is me. But the other time it wasn't me. Okay, so the problem is that mathematics is meaningless, but it's a problem with mathematics. It's not really a problem for mathematics. For mathematics is great. Because when a mathematician solves an equation, it doesn't really matter whether the equation is about physics, economics, biology, because the symbols don't care. Because mathematics is meaningless. That's why it's powerful. But if it's not a problem for mathematics, it's a problem for physics. Because if all we have is the math, then we quite literally, we don't know what we're talking about. And you must say, well, okay, fine, you're kind of exaggerating. We kind of know what quantum mechanics is about. I mean, we can make calculations. We know how to relate them to experiment. And yes, we don't know the details, but you know, for all practical purposes, we're fine. And for God's sake, Gabriel, you're an engineer, so what do you care about so much? Well, I think I care because engineers have to respond to a law that is a lot more important than the laws of physics, a law that is really a fundamental principle of engineering. Murphy's Law. Everything that can go wrong will go wrong at the worst possible time. And again, you can take this as a statement about how the world works, and certainly it's true. But really, Murphy's Law is really, really more than that. Because you see, most people spend most of their time getting something to work. And when they have something that is working, we're done. Well, these are not engineers. Because to an engineer, getting something to work is the easy part. Is getting things not to explode when things go wrong, that it's the tricky bit. Because you might be tempted to say, this case is never going to happen, or the user is never going to be so stupid to do that. And that's why you have Murphy's Law. Everything that can go wrong will go wrong, and you have to be prepared. Murphy was an aerospace engineer working on safety critical system. So this wasn't a joke. And let me give you just a silly example from my own practice. So at some point I was working on a physics experiment, and I had to write the code that read a configuration file and connect it to a database. And again, that thing can also fail. And so what you do, you code a nice error message. I'm trying to connect to database location. Are you sure the address is correct and visible over the network? You see, you try to cope with the failure and give the best possible thing to the user so that he can go proceed. Now, 2 months after I left the job, the physicist that took over called me and said, I'm getting a strange error message. Could you come to my office and help me out? So I go to his office. I open up the log and I read, I'm trying to connect to database location. Are you sure the address is correct and visible over network? And so I ask him, are you sure the database location is correct? And he says, oh, no, that's changed. Okay, so why did you call me? I mean, the error message was there. It had all the information. Why did you call me? Oh, I thought it was just a bogus error message. I didn't read it. So you see, an engineer is someone who addresses failure before they happen, while I guess a physicist is someone who ignores failures unless he can't, and then he calls an engineer to read them. So this is really why I am interested in the detail of the math, because engineers are paranoid with failures. And if I don't understand the model, if I don't understand the math exactly what it's saying, I don't know when or how I will fail. And Murphy's Law tells me it will fail at the worst possible time, probably when I'm under the shower. And so that's basically, what I'd like to have, just a good understanding of what the math is, like we have for other different physical theory. For example, take thermodynamics. Now then we understand, there is this thing called entropy. It never decreases, and if the process is irreversible, then it increases. For example, you may have noticed that it's relatively easy to turn a cow into hamburgers. Now, you may have also noticed that it's relatively difficult to turn the hamburgers back into a cow. Now, that's because of entropy. Entropy is disorder, and the universe proceeds from order to disorder. So left to their own device, things go from bad to worse. So basically, this is the physics analog of Murphy's Law. I won the lottery, I'm set for life, plenty of friends and a beautiful wife. All that I want I will do every day, so you ask, why am I this way? Oh my dear friend, it's an easy explanation. All of this goodness brings no consolation. It doesn't matter what we do or say, it is just another delay. 'Cause sooner or later we're all going to die 6 feet underground. I wave you goodbye, reversing this process is pure fantasy. There's no going back with entropy. So the universe is destined to chaos, and there's nothing we can do about it. Global warming, pollution, and deforestation. We must save the planet for the next generation. Recycle, save water, save energy and such. And you ask, why don't care so much? 'Cause sooner or later the earth will decay, the sun will expand and boil oceans away, and all that you see will turn dust or debris. You can't save the world from entropy. So again, this is all fairly well understood. That's what the physicists tell us. The physicists. Maybe we should double check. Trust but verify. Trust but verify. So, for example, we can have a glass of water and a glass of of vinegar. And this is a very stable configuration. All the molecules of water on one side and all the molecules of vinegar on the other side. Then, of course, we can mix them. We can put them together, stir, and as this is happening, the entropy is going to increase until we get to equilibrium, which is the highest entropy. And this is exactly the state where all the molecules are jumbled up. So it works. Entropy, indeed, is the state with the highest disorder. Except, suppose that we have a glass of water and a glass of oil, and again, this is a very stable configuration. Now we mix them, we put them together, and we stir, and we wait for the entropy to go up. But now, what happens at equilibrium is that all the water molecules are down, and all the oil molecules are up. And this is still a high entropy state. So how can I say that this and this are both maximizing disorder? It doesn't really seem to work. And to be fair, if you look at the literature, you find a lot of physicists that tell you, no, entropy is not disorder at all. It's information. And then if you look at the literature, you also find other physicists that say, no, entropy is not disorder, it's lack of information. Anyway, it's about information because Claude Shannon, when he derived this mathematical theory of communication, he derived the formula for entropy, he derived this expression here, and he called it entropy. So entropy is information. Now, funny story, do you know why Claude Shannon called this formula entropy? We actually know because he told us. You see, my greatest concern was what to call it, and I thought of calling it information, but the word was overly used, so I decided to call it uncertainty. And when I discussed it with John Menotti, he had a better idea. And John Menotti is a genius, of course he has a better idea. And von Neumann told me, you should call it entropy for two reasons, guys. We get two reasons. First reason, in the first place, your uncertainty function has already been used in statistical mechanics under that name, so it already has a name, which makes sense. Okay, there is already the expression, already has a name, why call it something else? In the second place, and more important, no one really knows what entropy is, so in a debate you will always have the advantage. This is a terrible reason. So, you see, I was naive. I thought that all of this was settled, right? And then we do a literature search, and then what we find instead, that there are lots of people with their own idea debating fiercely that there is better than the other, which is basically like the for interpretation for quantum mechanics. And we had a student report on one of these approaches, and I couldn't understand a thing, and I thought, it must be the student. So he takes out of the text, and it wasn't the student. 10 people in the room could understand what the author meant. So we really don't understand what entropy is. We don't really understand what fermatica is or anything of that. We have a bunch of recipes and tools for calculation, which is very, very useful because we can do a lot of things with it. But at the end of the day, it's all math. And math is meaningless. And so you might say, well, yeah, of course, nobody knows what entropy is, but you know what? Entropy and thermodynamics, statistical mechanics, they're not fundamental theories in many ways. So why do you care about those things? The important things are mechanics, field theories, and all of those are based on a Lagrangian. Now, the Lagrange is an important thing. So, for example, the standard model of particle physics, the one that defines all our interaction of the particle, is defined by a Lagrangian. And the symmetries, guys, the symmetries of the Lagrangian, they define all the quantities, the charge, the energy, the momentum, U1, SU2, the Lorentz group. Wow, the symmetries of the Lagrangian. You know, if you're like me, you're probably wondering, what is a Lagrangian? And if you open up a textbook, you find that the Lagrangian is a function of position and velocity. You give you position, velocity, and gives you some number. Okay, what is that number about? Well, again, the textbook is going to tell you that it's kinetic energy minus potential energy. Good. I understand what these things are. You can measure them. So, okay, so we understand what a Lagrangian is. Good. Except, this is a Lagrangian for a charged particle, and this part, 1/2 mv squared, is clearly the kinetic part, and this part, QV, is clearly the potential energy. But what is this thing in the middle? There is a V, so there is a velocity. Is it kinetic? But there is also the magnetic potential. Is it potential energy? Also, come to think of it, mass is energy. Is it potential energy or kinetic energy? And photons also carry energy. Is it potential energy? It doesn't seem that all the energy fits into this category. Plus, the Lagrangian is not unique for a system. If you have Lagrangian for a system, you can just, a derivative of an arbitrary function, you have a new Lagrangian, that works perfectly fine. And so it really doesn't seem that we know exactly what a Lagrangian is. And if you ask a physicist, he may say, but you know what, the action is really important. The Lagrangian is less important. The action is what is important, because that, the principle of least action tells you actually what are the trajectories that nature is going to take. Because this is how it works. You have an initial configuration and a final configuration, and all the possible paths that nature could take from the initial configuration to the final configuration. And each path is assigned an action. And nature is so efficient, is so parsimonious, that it's going to select the path with the least action. You see, the action is really the important thing. And if you're like me, you're going to be wondering, okay, what is the action? If you look at a textbook, you find that the action is the integral of a Lagrangian over a path, which means it's the average Lagrangian over a path with times the time interval, which we don't know because we don't know what the Lagrangian is. So at the end of the day, the action is just the thing that gets minimized during motion, in the same way that the entropy was the thing that got maximized at equilibrium. And so again, we don't know what these things are. All our physics that is based on the Lagrangian and the principle of least action is based on things we don't know exactly what they are. And again, we have these recipes that are very, very useful. We can make computation, we can make prediction, all very useful. But at the end of the day, it's all just math. And math is meaningless. Okay, and so you might say, well, okay, fine, whatever. Yeah, sure, math is meaningless. We don't know exactly what all these things are. But we do have the math. And the math is precise. It has been checked by a mathematician. And it's correct. So regardless of whether we don't know exactly what the math exactly is, we have a solid foundation because everything checks out. And again, I don't know, there is another tiny problem here, because how can you say that the math is correct? If we don't know what the symbols mean, how do we know we have the correct math for the physics we want to describe? I'll give you an example. Let's go back to the F equal ma thing, right? Again, this is just math. We know that m is a real number. Fine. But it can't be any real number. Because if I have a mass and I apply a force, the acceleration is going to be in the same direction of the force. So the math cannot be negative. Physically, this has to be either from 0 or greater. It can't be a negative number. And negative mass would not make sense. And we know, because we know what a force is and we know what the acceleration is. But if we have a Lagrangian and we don't know what it is, how do you know which Lagrangians are valid for a physical system and which are just mathematical junk, like negative math? So these are the things that I worry about. So for example, I could take the Lagrangian is equal 0, and then I have the integral of the Lagrangian over a path, which is always 0, which means that no matter what initial configuration and final configuration I have, all the action is 0, and nature selects the path with least action. But which one? Because they're all the same. And so, unfortunately, these type of things, physics textbooks don't really tell you that much. Some of them is going to tell you that a Lagrangian needs to be hyperregular, but it doesn't tell you why. So I started there, and okay, let me try to prove it for myself, and I could solve proof to myself a simple case. I couldn't prove myself the general case, but then I said, look, you're being silly. This is math. The math is being checked out, so you just follow the citation and see what they say. So I follow the citation, and all the books that I found, they go back to this book here. And this is the page where it proves that the Lagrangian has to be hyperregular to get the single solution. But there is a problem, because if you look here, it says, in deriving 54, we assume that F is a symmetric matrix. And this is the simple case that I was able to prove by myself. So this is no better than what I was doing, but there is a footnote. Okay, so let's look at the footnote. The footnote says, without this assumption, which is unnecessarily restrictive, equation 54 and 55 become more complicated. I know, that's why I'm here. But it can be shown that theorem 1 and 2 remain valid. Okay, so let's see how the math checks out. Private communication. So it seems that the guy wrote a letter to the other guy, they agreed that this would work, yeah, it's fine. And after this, I can tell you I don't trust citations anymore. So it turns out that this actually I was able to prove, it checks out, but it's kind of, we're full of all these little problems. So for example, in quantum mechanics, you say that a state is a ray in a Hilbert space, whatever that is. And again, we have the same problem. Are all the rays in a Hilbert space physically meaningful, or it's like the negative mass for the negative mass or a non-hyperregular Lagrangian, so that there is mathematical junk there? Well, there is a mathematical theorem that tells you that there are always states for which not all average quantities are well defined. So inside the Hilbert space, you're going to find a state that have infinite average energy, which would be very useful for all our energy need until you realize it would just make a gigantic black hole for the whole universe. So it wouldn't work. And there are also states with undefined position that are tricky to measure because you don't know where to put the detector. So these theories, yes, we have the math, but it's full of mathematical junk, of things that are not physically valid, that don't make physical sense. And I used to blame mathematicians for this. Mathematicians are not giving us the correct mathematical structure. Bad mathematician. Not on the couch. But then I went to a topology conference, and talking to a topologist, I sort of told him my frustration with math, and he very simply said, look, I don't know physics, I'm a mathematician. I don't know what you guys need. You see, he's right, because, I mean, he does mathematics, so he deals with meaningless symbols. But the problem is that finding the correct mathematical structure for physics, it's not a math problem. It's a physics problem, because only a physicist would know whether the mathematical structure works or not. But the problem is that theoretical physicists have basically given up on this. And if you go to a theoretical physicist and you say, oh, there are all these things that don't make sense, and you say, just ignore them. This is the attitude. And he's going to say something like this. Well, you know, it doesn't really matter whether there are some objects in the math that are non-physical. The important thing is that the objects we need, the ones that are physical, are well defined mathematically. And that's always the case, always. Except this is the most popular formulation of quantum field theory, the best theory that we have for nature, is in terms of path integrals, which is again something about the action and looking at all the paths that something could take. But these paths are no longer a simple trajectory, they are evolution of fields configurations. They are mathematically much more complicated objects. And so to be able to define this integral well, you need a way to count all these possible paths. And mathematicians tell me that this is not well defined in general. So, if all we have is the math, we kind of don't really even have the math. We have a vague physical interpretation of meaningless, sometimes ill-defined symbols. This is what we have. Remember at the beginning when I said, oh, the word of the foundation of physics is really sad? This is what I meant. I mean, there is this aura of like rigor and precision in theoretical physics, but in physics. But you go and look underneath the surface, this is what you see. And the general attitude seems to be, well, don't scratch the surface, you're going to ruin the paint. And I have to say, this whole thing makes me very uncomfortable, especially when there are those people that say, I believe in science because science has a solid foundation. I don't know what to tell you. It makes me very uncomfortable. And so the problem is not simply what is the right interpretation of quantum mechanics. It's also, okay, what is the entropy, what is the Lagrangian, what is the action, what is the realm of applicability of all these theories, what mathematical objects are physical and why, when does physics end and math start, can we have a common conceptual basis for all physical theories, and what is a physical theory anyway? And the problem is that all these questions are interrelated with each other. You can't just pick one question and answer it in isolation. Either you answer all the questions or none of the questions. And this is the problem. This is a whole tangled mess. And so another question is, well, can we do something about it? Can we actually disentangle the mess a little bit? Well, for example, let's take these equations. These are the basis for the Hamiltonian formulation of classical mechanics. What are they describing? Who knows? It's difficult to see like this. But maybe we can find an expression that is mathematically equivalent, but it's easier to understand physically. And this is what we get. Assuming the original equation is equivalent to saying that the initial conditions of position and momentum are mapped one-to-one to the independent, mapped one-to-one between future and present, and that independent variables remain independent. And so that is to say that the evolution is deterministic and reversible. So we can either say we have those set of equations, or we can just say the evolution is deterministic and reversible. And so we have now a purely physical condition that describes the math exactly. We can recover the math, but we now understand what the math is describing. And it's not even that complicated. And with this now we can ask other questions. We can ask, are these equations universally valid? Well, if you have a system that is coupled to its environment, then the future depends on something else. The future state depends on something else, depends on the environment. And so the evolution is not deterministic and reversible, and so the equations do not apply. But technically, nothing is ever fully isolated. Everything affects everything else through gravitation. Therefore, these equations are approximations. They're not true, they're not the true equation of the universe, they're pretend, but they're useful tools, they're useful models, and that's why you use them. Man, I need more water. Let's hope I don't kick this and make a mess. So the idea here is that we started with the physical theory, with the math, and we reversed engineering some assumption from which we can rederive the law. And this allows us to reason in terms of physical concept, determinant reversibility instead of math, instead of partial derivatives. And we can get our philosophy straight because we can finally know what we're talking about. So the idea is that we can disentangle the mess, we can understand all of this much better if we reverse engineering the law of physics, if we recover the underlying principle, and we call this approach reverse physics. So let's go back to one of my old questions. What makes an object a classical system or a quantum system? So suppose you have a ball. Now you can throw it and you can study its motion, or you can also take a red marker and make a red dot and study the motion of the red dot. Studying the ball is equivalent to studying all the possible red dots. And classical mechanics assumes we can make these dots as small as we want. So the system, the classical system, is infinitesimally reducible. Studying the whole is equivalent to studying all its arbitrary small part. That's what a classical system is. Now suppose you have an electron. Now you can study the electron, but you can't take a red marker and make a red dot on the electron. You can't interact with only a part of the electron. Either you interact with the whole electron or none of the electron. So you can't describe its parts. The system is irreducible, and this is the assumption underlying quantum mechanics. And again, this is an assumption. So remember how we said that even complex objects can act as single quantum system? Well, suppose you have a proton. If you probe it at low energy, the resolution is coarser than the size of the proton, so you can't resolve the internal structure. Nothing can depend on the internal structure. The system can be assumed to be irreducible. But if you use higher energy, then you can access the internal structure, and the system can no longer assume to be irreducible. So you see, a system is not intrinsically a single quantum system, a composite quantum system, or a classical. It depends on the assumptions that are relevant in the particular circumstances. And if you recall, many are puzzled by the fact that quantum mechanics has two laws, one for the evolution and one for measurement. Well, quantum evolution is Hamiltonian, like we said before, so it applies only when you have a deterministic and reversible process. And when the system is isolated, and so during a measurement, you must couple the system with a measurement device, which is in the environment, and so the system is no longer deterministic and reversible, therefore the first equations do not apply. We are out of its realm of applicability. And so these are reasonable answers that don't need the parallel universes, hidden variable, consciousness. We just have some models, and these models work under some assumptions, and if the assumptions are not satisfied, then the models do not apply. There is no mystery. And so in a way, in a precise way, the model is actually the assumption, because we can rederive the model from the assumptions. As we discussed before, the Lagrange and then the action, can we also understand what the action is? Can we understand this thing that is at the heart of many physical theory? And the answer is yes, but it's a little bit technical. And I would need a lot more time to tell you what all those things are. But I figured that if you simply memorize this, you still know more than the average physicist. No? Hey, I went to a comedy show yesterday and I learned that the action is the line integral of the vector potential of the flow states. Cool beans. What? You don't know that the action is the line integral of the vector potential of the flow states, and you study theoretical physics? Now, it's a little bit difficult to remember, but I thought we can try with some music. We can have something like, the action is the line integral of the vector potential of the flow states. Now, everybody together. The action is the line integral of the vector potential of the flow states. Again, the action is the line integral of the vector potential of the flow states. Very good. So now you know more than most physicists. Now, reverse physics allows us to deconstruct the equations and make the find the physical assumptions that are underneath, and this is all great, but it's not enough. As we said before, we still need to figure out exactly which mathematical structure are appropriate for physics. For example, we have real numbers. Well, when can we use real numbers, and when can't we? And I said before, when you study physics, you get a sense that it's the job of the mathematician to get the correct structure. And so, for example, I found this in Wikipedia, so it must be true. So at the top, there is the perfect, immutable math. And from math, everything descends. Mathematical physics descends from math, and it's a subset of math that we apply to physics, and it's kind of lesser math, it's kind of dirty, less pure. And from math, we also get an ontology, which I have no idea what it means, but it's on Wikipedia, so we can't argue with Wikipedia. And then, at the end, we get, physics, the bastard child of math. That's sort of the picture that a lot of people have in their head. And if you have two neurons and you connect them together, you kind of see that this does not make sense. What would make more sense is something like this. You have physics on top, because that's what we're doing. And you start with physical principles and physical assumptions. And from these, we get the requirement for a particular system in a particular case. And we also get the semantics, the meaning, because we start by knowing what we're talking about, which is kind of useful. And then we turn these requirements into math, in rules about symbols. And since the symbols are meaningless, the semantics does not reach the math. And we can call this physical mathematics because it's mathematics that is correct to capture physical systems. It's meaningful math. So this is, I think, how things should work. And let me give you an example of something that we've figured out. So one of the pillars of the foundation of mathematics is logic. And logic is about statements. And the rules of inference and math is about proving the truth or falsehood of some statements from other statements. Now in physics we also have statements, but their truth is not proven, it's found experimentally. So what we need is really experimentally verifiable statements, things that have a test, and the test finishes in finite time if and only if the statement is true. But these statements follow some different rules and don't have the same rules of standard logic. So for example, take the statement, there exists extraterrestrial life. If we find it, then the statement is verified, we're done. But if we don't find it, we can conclude that the statement was falsified because absence of evidence is not evidence of absence. So the only thing that we can do is to keep looking, and the thing is never going to terminate. So the negation of a verifiable statement is not necessarily a verifiable statement. And so from these ideas and from the logic of experimental verifiability, you can recover two mathematical structures, topologies and sigma algebras, that are very abstract and most physicists wouldn't know what they are, but they are at the foundation of all the other things that we use in physics. The real number, calculus, probability theory, differential geometry, they're all based on those two structures. Now, and it makes sense that all structure that we use in theories, in physics, would have topologies in sigma algebra, because physics is about, again, things that are experimentally well defined. And so it makes sense that all these structures capture experimentally verifiability at a fundamental level. And everything that you get here is really a dictionary between the math and the physics, so the proofs are not about meaningless symbols anymore, they are about what can be discovered experimentally. So it's not just math, it's physical math, it's meaningful math. And so reverse physics and physical mathematics, they can tell us something very deep about physics. So for example, if we start with this idea of all the things that can exist, and we call this the metaphysical world, a smaller set is the set of all the things that we can interact with, and we can call that the physical world. But even smaller is the set of things that can be tested with a reliable experimental procedure, and we can call this the empirical world. Now, topologies and sigma algebras only apply to the empirical world, not the physical world or the metaphysical world. So all our physical theories are only about the empirical world. Instead, hidden variables, parallel worlds, they're not in the empirical world, they are in the metaphysical world. But then it makes no sense to use the same mathematical tools we use for the empirical world, but yet people do give topologies and hidden variables they give topologies to hidden variables and parallel worlds. So they use the tools that are for the empirical world for things that are in the metaphysical world. And again, they do this because they don't worry about the level, the realm of applicability of models. They don't worry about Murphy's law. And so there is another thing that it's not in the empirical world, which is God. You can't prepare God in the lab. Yesterday I went in the lab and I prepared 10 Zeuses. That doesn't work. And again, it's just because it's not in the empirical world. So science can't tell us anything about it. Because science studies objects in the universe, and God is not an object in the universe. And science studies objects in the universe, so science doesn't study God. Science studies object in the universe. God is not an object in the universe. Science studies object in the universe. Science doesn't study God. Science studies object in the universe. God is not an object in the universe. Science studies object in the universe. Science doesn't study God. Science doesn't study God. Science doesn't study God. But physical theories are not even about the empirical world. Because, as we said before, we use assumptions like determinant reversibility, infinitesimal reducibility, and we know that these cannot be realized in practice. They're technically wrong. So physical theories are idealization, and in fact, I don't even think we can write a mathematical theory without having some sort of idealization. And if you remember, I told you that most people that work on the foundation of physics are interested in reality itself, what the constituents really are. They're interested in the metaphysical world. But this is not what physics studies. Physical theory are idealized account of the empirical world. So yes, physics talks about what it exists, but equally important are the requirement of experimental verification and the role of idealization. So if you just focus on reality itself, and you're disregarding 2/3 of the problem, and the physical theories, like quantum mechanics, become strange and mysterious. But then if you recognize that physics is about idealized account that can be studied empirically, then the math is justified, you can get back to it, and the physics make more sense. And surely people in academia are going to be thrilled about all these things, right? Because you always hear that people in academia support thinking outside the box, that interdisciplinary is so important and crucial, and everybody wants new ideas, right? So if you study marketing, you know that you should never enter a market when there is no competition. You want to enter a market where the competition exists, but it's bad. Now you may naively think a market without competition is better, but the issue is, why is there no competition? I mean, it could be that your idea is so new and original that nobody thought about it, or, much more likely, other people had your idea, tried, and went out of business. There is no competition because there is no market. Nobody wants your idea. Now, it's the same way in academia. If nobody is interested in your research, either you change research topic or you starve to death. So either way, you're not going to do the research. Now, a lot of the idea that I just summarily presented here are, in retrospect, simple. So there is no technical reason why a lot of things that we have developed couldn't have been developed decades ago. And granted, things that are simple in retrospect are not necessarily simple to find. And granted, I am a genius, but I'm not the only genius. So, Occam's razor, the simplest explanation would be that this hasn't been done because there is no market. So we should check that. So how does academia work? How does the market of academia work? You see, I didn't even put this down. Very nice. Okay, so suppose that you figured out that the logic of experimental verifiability leads to all these topologies, single algebra, that are a foundation of all the other mathematical structure, and you think, we can create a general mathematical theory for experimental science or all of these things. How do you proceed? Well, you write a paper. You write a paper, and the first thing that you do is you put it on the archive, on the preprint server, so that you put there the draft that other people can comment and have learned discussion. And so this is what we did, towards the general mathematical theory of experimental science. And you can see here there is already a little bit of a problem. The category says computer science, artificial intelligence. I didn't put it there because it's a physics paper, but somehow the people that manage the archiver decide that this is not physics, it's computer science for some reason. Okay, so this does not bode well already. But okay, then we try and we say, okay, we need to publish this. Let's find an appropriate journal for this. And we find a journal that is there is a forum for discussing the conceptual structure and foundational aspects of physics. This seems good. So we submit this, and we get what is called a desk rejection. Basically, the editor looks at it and says, well, this does not relate to current discussion. People are not discussing these things in the foundations of physics, so we're not interested. But this does not mean that your work is not interesting, so it should be done, just somewhere else. Somewhere else, perhaps in a theoretical physics journal, maybe would be more suitable, so you submit to another journal that publishes research on the mathematical structure that describe fundamental processes of the physical world. That seems a good fit. Unfortunately, we do not think that this is appropriate for our journal. So we go like, I don't know, half a dozen journals until we do find one that is interesting in publishing, but it says as the Heinrich Associate Editor feels that even though the subject matter is of interest, unfortunately our journal could not find appropriate reviewers. So again, it's too different from what people do, and so what is this thing? I don't know, somebody else should look at it. And again, so we said, well, maybe a more mathematical oriented journal. Again, do the research just somewhere else. And of course, this is not math, so it's not going to go there. And so what you learn is that this approach doesn't work, because if what you're trying to do is too different from what people are already doing, you just are not going to get published. You only small modifications. So okay, this is not God's strategy. So let's try a different strategy. We should take a nice result that we have that should be interesting for physics and just publish that. So something smaller. And you may not know this, but we figured out that the action is the line integral of the vector potential. So we said, why don't we publish this? Okay, so here is the preprint, geometric and physical interpretation of the action principle, and it's in physics, classical physics. Okay, good. So this should be an important result. Let's find a prestigious journal, one that publishes paper of the highest qualities, and the content reflects core physical discipline, and there is no more core than this. And so we submit this, and we get another desk rejection, because it seems that this should be interesting for the people that work on foundational physics, but not anybody else. And I guess the thing that I don't understand here is that most people that do physics at some point are going to have to teach this stuff. And I thought that understanding what something is would make it easier to teach it, but I guess that's just my... but the thing that is even more interesting about this rejection is this part. I regret that we not feel that the paper represents the significant level of new physics that would be likely to excite the immediate interest of researcher. So prestigious journal, this is how they select things, whether they excite the immediate interest. I read your paper and it's like correct, but it's like not exciting. I don't feel excited. This is how they select paper. So, okay, well, foundations of physics, let's go back. We have a forum for discussing conceptual structure and foundational aspects. Surely they're going to be interested. I know. The above submission has been rejected. And again, these are all desk rejection. It never went to review. It's not that it's wrong. It's just we're not interested to know what the Lagrangian and the action, the principalist action are. This we're going to cut it because it was a mess. Okay, so at the end of the day, we do publish this thing. We publish it in what is called a catch-all journal. They don't care whether things are interesting. We'll just check that it's correct and that you have the 3,500 open access fee. And this is still a prestigious journal from the same company that does the other prestigious journals. So, And at the end of the year, we get a notification that our paper was among the top 100 downloaded articles out of 22K. So it would seem that there is some people that would be interested to know what the principle of reaction and the Lagrangian are. In fact, if you look at the number, this is our paper that this got 30,000 accesses. If you look at 10 more exciting papers from the other journal, they get less than half of what we make. And so you would think, but then this is exciting, people. No, because this metric in academia is worthless. The thing that is really interesting and useful in academia are citations, how much other people that write other papers talk about your paper, And apparently Buzz, the social media news article Wikipedia mention. And we only have one citation, which is still us, so it doesn't count. So you see that all the citations are basically better, and the Buzz is better. So even if you have a big result, it seems that it doesn't really do you so much, because at the end of the day, citations are the currency of the academic market, and if you don't have a market, if you don't have citation, then you're out of the market. Because this is how it works. Suppose that you want you want to have some people working on something in academia. Well, these people are gonna need citations for their work. And where do they get from citations? Well, from other people that work on the same thing. But before they can get citation, they need their work to be positively reviewed. So you need reviewers. And where do you get reviewers? From other people that are working on the same thing. But before you can review it, they need to be sent for review. So there has to be a journal that thinks that something is interesting. And when will a journal think that something is interesting? When there are lots of people working on it. So basically the conclusion is that you can't work on fixing the underpinning of the current physical theories because there is no one working on fixing the underpinning of the current physical theories. But if there had been people working on fixing the underpinning of the current physical theories, they would be fixed. And we wouldn't need people working on fixing the underpinning of the current. So either way, we can have people doing this. And this is a significant problem. But it's not the only one. Because you see, again, I was naive. I thought that when you start working on these things, you're going to have learned discussion with people. Instead, this is a typical email that I get, completely unsolicited, from a guy that I don't know. I have admittedly only superficially read your paper on the physicality of Hilbert spaces, apparently for quantum mechanics. I wonder if you are telling anything new. Moreover, it is already clearly pointed out by blah, 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 lots of citation, yet none of this is mentioned in your paper, and I can't help wondering why. You know why? Because it's all irrelevant. All these citations had nothing to do with the main point of the paper. And then he says, in all, I can't help but take a very critical attitude towards your paper. So the conversation goes on, and it ends with this sentence. Well, since you know the literature, I can hardly add anything of interest at this point. So you see, he wasn't even interested in really the merit of the discussion. He was just irked that I didn't cite the literature useless that he liked. And I mean, to be fair, it's not an unreasonable request to cite appropriate literature, but the problem is that when you're doing something like this, it's very interdisciplinary, you're going to touch 10, 20 different subfields, and if every single subfield has their own literature, most of it is going to be irrelevant. If we had to read and cite all these irrelevant literature, I would probably die before we get anything done. And this is one of the problems, is that we need to pull things from all different branches of math and physics and computer science and engineering to get a synthesis of all of this. And, oops. And you can't be an expert in everything. And the issue is that I try to go to expert to get some advice, but things don't always go as I'd like them to go. So for example, this is a typical email that I would send. Yeah, I'm a researcher in the physics department of the University of Michigan. I'm looking for a source. I found the pages to be very useful, and you seem to be one of the main maintainers. Let me thank you for your work. And there are, however, some construction I'm missing. For example, I need, and I'm wondering if you have encountered such construction, right? So I'm basically going, trying to tell and to fish some feedback. So, and most of the time, people don't reply. 90% of these emails get replies, 5% are going to give me completely irrelevant citation, but this particular guy replied. And it's a good response, because he says, thanks, I used a lot in the work and citation, and it's a good citation. It's actually a citation that is relevant, that I can use. And then he is trying to understand what I am, not sure what the concept would be, so I'm trying to guess what you really mean, so he's trying to engage. And this is very, very rare. So I reply back and I say, this is excellent. This is excellent. Your citation is excellent. And this is what you mean? No. But I've attached the relevant part of a draft I'm putting together. And the definition I currently have is simple enough. And I changed the notation to follow your definition. So hopefully it should be fairly straightforward. And I hope the examples are enough to give you a sense of what I'm trying to do. It's basically one-page PDF with 3-4 lines of definition and 3 examples so that you can get, right? And he replies again. And he says, your definition is clear enough, but there are some problems. So it doesn't seem like a very useful notion unless this is very fair, this is the behavior that you want. And this is strange, because if you look at the examples, that problem doesn't happen. And so I reply and say, I don't understand. Are you saying the examples I give is wrong? And he writes back and says, I didn't read your examples. And then the conversation becomes more and more confused, and I say, look, I'm not married to that definition. If there is a better definition that does what the examples do and fixes other problems and is already known in the lecture, I gladly use it. That's why I'm here. That's why I'm talking to you, you the expert. So my question is again, are you aware of such a definition? And he says, no. And he adds, can you give me an example? How could you ask? I asked you for a definition that works with the example. How can you ask me for the example? And so I gave up. And half an hour later, never mind, you gave me some. And so these are the experts. And at the end of the day, what you have to do is try to become yourself an expert in everything, which you can't do. But it's even worse than that. So I was at a conference, and there was a guy talking about generalized probability theories. And again, the idea is always measurements are in terms of probability. So both classical and quantum mechanics are just special instantiation of a more general probability space. And these are the type of things that I would be interested in. So, but there was a technical problem, so I go to him after the talk, and I tell him, look, you're working everything with discrete variables, and I don't understand when you're going to make the limit how you're going to get the correct sigma algebra for the continuum, because it doesn't seem that that's what you're going to have. And he looks at me and says, I don't know what a sigma algebra is. Okay, so the sigma algebra is one of the three things that you have to define for a probability space. And you say you are generalizing a probability space, and you don't know what the sigma algebra is. What is it that you are actually generalizing? And this is the issue, is that people are expert, but only in their little domain, and then even if you go a little bit, you just have some holes, and you already have problems like this. And again, this is because academia is all made by all these silos that don't talk to each other, and it breeds misconception and mistrust. So, for example, I was at a school of philosophy of physics, and I was trying to engage with the graduate students there, and one of them, out of the blue, says, well, but in the end, physicists don't understand anything about the foundations of physics. And so I said, well, look, I just came out of a conference in physics where there are people working on high precision measurement, quantum information, quantum optics, and so on. Are you telling me that all of them didn't understand anything about the foundation of physics? And he was, fishing for some kind of, clarification or something. He said, yes, all of them, they don't understand it. And now, you are working on philosophy of physics, and you think all the physicists don't understand anything? I think you have a problem. But this is essentially what happens, is that academia is really built into these different silos of different disciplines. It's very difficult to go from one to the other. And what we're trying to do is very interdisciplinary, because at the end of the day, nature does not care about these differences and limits, but academia does. And even worse than that, whatever you do, you need funding. You need money. And there aren't that many funding agencies that fund basic research in the US. So the biggest one is the Department of Energy. And these are the categories. Because you don't just apply to what you want, you have to apply to one of these categories. So let's say that you want to create your general mathematical theory, blah, blah, blah. Where do you ask for money? Advanced scientific computing doesn't work. Materials chemistry, that doesn't work. Fusion, there is no category. So it's not that you don't get funding. It's like you can't even apply for funding. So if we wrap up, Or if you want to create something like this with all the math and physics figured out, all you need to do is be technically expert in a dozen fields spanning math, physics, engineering, computer science, and philosophy of science. And then you, of course, you have to do the actual work of combining all this technical knowledge into a coherent picture. And then you have to communicate the results in pieces to each field in a way that excites them individually, using their language, citing their literature, and even if it's irrelevant. And then you have to engage with people that most of the time don't respond, are far too busy, and maybe not knowledgeable enough, and are not interested, and sometimes full of themselves. And you have to do all this without any stable sources of funding. So it's pretty clear why we don't have a nice foundation for physics. Because you see, most academics are very reasonable people, but they work in a system of incentive. They have to get their PhD, they have to get their citations, they have to get tenure, they have to get grants. And all this system of incentive is really designed to not even make you start in a project like this. And so this is the problem. It's kind of sad, but this is how it works. So, can the work be done? Well, technically, I think it can be done because we proved that the most difficult part is always starting. So we have a starting point. And so it can be done. And will it get done? Well, the odds are against it. And I was discussing this problem with my old university classmate that stayed in academia. And their conclusion that you'd need someone from the outside to invest in the project so that you could hire the right talent and build an interdisciplinary team. But the problem is, who is going to fund this type of things? Well, it's funny because there always seems to be money for crazy ideas that are likely to go nowhere. I don't know if you remember the Google glasses, which everybody's supposed to be used. I don't think I have them. Or the metaverse, right? There's also money for the metaverse. Or NFTs, non-fungible tokens. These monkey drawings were worth $400,000, and then they, dropped after a few months. And this is a message from one of the experts in the business that says, "I told my friends to buy at 300K. I'm happy they didn't listen to me." So there always seems to be money for things like this, things that excite the immediate interest. Things that are super exciting, that type of thing. But for things, that go in the detail, all the boring detail, there doesn't seem to be money for that. You work on a great innovation that's applauded by the population. You invite the investors for a big demonstration. Nobody cares, nobody cares, nobody cares. But if you're hip and you are in the loop, you can sell anything as a scoop, even if it's poop. People from every stripe therefore can buy into the hype like rats enchanted by your pipe. If you're cool. Okay, maybe it's not exactly like that, I'm sure it's not like that. But it kind of feels that it's like that. And it thinks that the more egotistical and the more money and attention you get, and even if you fail or engage in questionable practice, no consequences. You always pay for what you take. You always stand by what you make. But then one day you make a single mistake. Your life is ruined, your life is ruined, your life is ruined. But if you are important and in your prime, you'll get a free pass every time for every crime. They'll love your dirty jokes, and even if you'd kill some folks, you probably wouldn't lose any votes if you are cool. And that's how the world works. And I can't change that. And I can't beat them. And so I thought, maybe I should join them. I'd have to stop doing the actual work, but I have to be hip, memorable, excite the immediate interest. I'd have to be cool. But how would I do that? Well, what if I put on a show? I mean, I can play the piano, I can act like an idiot on stage, and I can tell a few jokes and write a couple of songs, and maybe member of the audience will be dazzled, inspired, and excited. Are you excited, guys? I'm super excited. And they will tell that there is this amazing genius that is solving the foundations of physics. But how do you know? Well, because he told me. And he sings and he tells jokes, and surely he must know what he's talking about. Plus he figured out that the action is the line integral of vector potential. So now it's up to you guys. Have we become hip and cool and exciting? And tell your friends, tell your favorite influencer, tell the newspaper, but most of all, tell the billionaires. Tell them to give me lots of money, lots and lots of money, that I will solve all the problems in the foundations of physics, because maybe this time it won't be a total scam. And that's the show for the evening. Thank you, guys. So I have 3 questions for you, because this is a big experiment. 1, was it entertaining? Yes. Okay, good. Did it make you think? Yes. Did you learn something? Yes. Good. So I'll give like a couple of minutes if there are some people that had enough and just want to go out. I'll be here for questions if people want to ask questions. Otherwise, again, thank you again for coming. You've been great. And thank my wife Cristina Dalla for having me organizing, and my son Matteo and Charles son here for the hard work, and for all the other people that have me organizing. Thank you so much.